So let's think of an example with the Chow test, or kind of go through an example where the steps that you would take to do this Chow test. So say we're interested in CPGA, so cumulative GPA. We think that's a function of maybe your SAT scores. Maybe it's a function of high school GPA. And maybe it's a function of the total hours you spend studying, plus you. And maybe we want to test whether this regression function is the same, and if we have two different groups, someone who identifies as female and someone who doesn't identify as female. Let's say we have two groups. Identify as female, do not identify as female. Or we could do the same thing, identify as male or do not identify as male. And so here are our two groups. And let's say we want to test whether they have the same intercepts and slopes. So our null is that both groups have the same slope. And HA is at least one of the slopes differ. So, I changed a little bit here in that before our null was that the slopes and the intercepts were the same. Where here I'm allowing the intercept to be different between these groups, just to kind of show you what it looks like. And so let's think about how you do a Chow test on this. Okay, so here's our regression. Let's call this, regression 1 again. And so the SSRR, which is often called the SSRP for pooled, because we're pooling everybody in our sample, is the SSR from the following regression. So what's true when this null hypothesis is true, right? We want to put in our restriction. So let's write out what our regression would be. Maybe I'll say A for the steps. So we'd run a regression where CGPA equals beta 0 plus delta 0, and I'm going to put female here. What this is doing is allowing the intercept to be different across the groups. If we didn't want to allow the intercept to be different across these groups, we need to get rid of that. So how we were doing it before, if we wanted the slopes and the intercepts to be the same, we wouldn't have this in our regression. But because we're allowing the intercepts to be the same, the intercepts to be different, we need this term in here, because this is going to allow, remember, the intercepts to be different. And then we just have our normal regression. Beta 1 SAT plus beta 2 high school GPA plus beta 3 total hours plus U. And we'd run this on people who identify as female and people who do not. So we're gonna, if our entire sample is just people who identify as female and people who do not, we're gonna run this regression on everybody in our sample. So let's say if this was, NF for number of female, and this is NF for number of not female, then it's going to be both of both of these groups are included in this one regression. And this term here is just allowing the intercept to be different, like our null is trying to allow the intercept to be different. So that's the first thing we need to do. It doesn't have to be the first thing, but that's one of the things we need to do. Then we need to run regression 1 on just people who identify as female. So that's one of our SSRs, so 0 or 1. And C, we want to run, the last thing you have to do, besides figure out the number of restrictions and the degrees of freedom, is run that same regression on just those who don't. Identify as female. We're going to call that SSR1 if we're using the same nomenclature as before. Hopefully I can fit it in, but now the Chow test is going to be, remember that SSR restricted or the SSR pooled. I'll put a P there to be consistent with your book. So it's the SSR from this regression. Again, we're allowing the intercept to be different, so it's a little bit different than last time. I just want to show you both kind of ways the Chow test is commonly run. And then we're going to subtract the SSR0 plus the SSR1. So this is like our unrestricted regression, which is allowing both the intercepts and the slopes to differ. And we're getting that by running this regression once on just those who identify as female, and once again as on everyone who doesn't identify as female. I guess I need another bracket there. Let's think about the number of restrictions now. Well, it's a little bit different than last time. I mean, one thing we could do is count up all the parameters in our restricted regression and think of all the parameters in our unrestricted regression. The difference between those are the number of restrictions. So here we have 1, 2, 3, 4, 5 parameters. Sorry, 1, 2, 3, 4, 5 parameters in our restricted model. In our unrestricted, we have 1, 2, 3, 4. But we have that times 2, right? Because we'd have different parameters for each of these groups. So that's 10. 10 minus 1, 2, 3, 4, 5 is 5. So the number of restrictions would be 5 here. Is that right? 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, 8. So whoops, we have 3 restrictions. That makes more sense because that equals K. A little bit better. Just figuring that out on the fly here today. So that equals K. So that's a little bit different than last time, right? Because it was K plus 1 as the number of restrictions. That 1 has gone away because we're allowing the intercept to be different. And the denominator is just kind of what it was before, SSR0 plus SSR1. Now degrees of freedom, so think of the total number of people in our sample. So let's say that n is both these numbers together. N, again, 1, 2, 3, 4. We have 4 parameters. So again, it's going to be 2k plus 1. This k equals 3. So this is n minus 2 times 4, which is 8, right? So 3 plus 1 in there, so n minus 8 is the number of degrees of freedom. Hopefully, oops, probably off the screen there. N minus 2, 3 plus 1 is n minus 8. Sorry, it's probably off the screen at the bottom. All right, so here's an example of running a Chow test where we're allowing the intercept to be different, but we're testing whether all the slopes are the same.